Okay, this is 6.5, exploring graphs of reciprocal trigonometric functions. So our goal is to graph the reciprocal trigonometric function and determine their key characteristics. So everything we've learned about trigonometric functions and everything we've learned about reciprocal functions, now we're combining those two lessons and looking at the graphs of cosecant, secant, and cotangent, which of course you know as the reciprocals of the regular trigonometric functions sine, cos, and tan. So it says, recall that the characteristics of the graph of a reciprocal function of a linear or quadratic function is directly related to the characteristics of the original function. Therefore, the key characteristics of the graph of a linear or quadratic function can be used to graph the related reciprocal function. The same strategies can be used to graph the reciprocal of a trigonometric function. So what are those key characteristics? Does anybody remember? So when we did this lesson originally, we looked at these two graphs. Okay? Does anybody remember what the original graph, y equals x, tells us about the reciprocal graph, y equals 1 over x? Yeah, Lyndon. Sorry? They're in the same quadrant? Okay, right. So when the values are positive, the values are positive. Good, that's one. So positive values produce positive values on the reciprocal. Right? Alan?
The zero of the original is the vertical asymptote of the reciprocal.
Excellent. So if this is my original, it's tough to see, eh? Let me write it over here. Original just doing a very quick review up here at the top. So we said positive values, they produce positive values. And vice versa, right? For negative. Okay, and the other one I heard was zeros produce vertical asymptotes. What else? Yeah, Joseph?
Wherever 1 over x decreases, wherever x is increasing.
Okay, right, so increasing values produce decreasing values, and decreasing values produce increasing values. Good. Anything else? Luigi?
When y equals 1 or negative 1, on the original, it remains the same point on the inverse. Or reciprocal, my bad.
Very good. You guys are on fire. Anything else, Jesse?
When n behaviors go to infinity, there's a horizontal asymptote by 0.
Good. Okay, I'm running out of room here, but when n behavior okay, there's our review, and that was from section. Anybody remember the section offhand? Reciprocal. It was in 5, right? Okay, so basically we're taking all that information we learned now, and I'm glad so many of you guys had all of that right at your fingertips, because that's important, because now we're just taking that and applying it to the trigonometric functions. Okay, so the first one we're going to look at is y equals sine x, which by now everybody should know how to draw this. This should be memorized, believe it or not, right? If you have it in grade 11, you need to by now. This should be, very easy to recognize. And you need to be able to do it both, in degrees and now in radians. So where there was 360, it's now 2 pi. Where it was 180 is now pi. Any questions about this graph? All right, good. So we're going to look at it a little closer. Okay. It says use this graph to predict where each of the following characteristics of the graph 1 over sine x will occur. So of course we know 1 over sine x is actually just another way of saying. Okay, everybody knows that, right? 1 over sine x is cosecant x, yes? Okay, I don't have to review that. Okay, good. So, so vertical asymptotes are going to occur where then? Where are these going to occur on this graph? Yep. Earth x equals 0, so vertical asymptotes are going to be good. X equals, well, let's start over here, right? We'll say negative 2 pi, negative pi, 0, pi, and 2 pi. Everybody see that? Is that those are the zeros on this axis, so they're vertical asymptotes on our reciprocal axis. Any questions about that? Sorry?
Can you explain?
Okay, wherever there's a 0 on the original, there's a vertical asymptote on the reciprocal. Okay, that's a review from chapter 5. Sorry, 1 second. One second, I just hit the wrong.
It's still recording.
Yeah, I know, it's still recording. Sorry. Okay, sorry about that. I had the wrong lesson up. Okay, so there's another way to express this, and this is important, guys, that you understand how to use this. We touched upon it yesterday, but we're using that n as an integer. We need to express this using kind of n as an increasing integer. Anybody know how we could do that? This is a really simple one. Look at the integer, negative 2, negative 1, 0, 1, 2. So how could we write this instead of writing it like this? Sorry? Yeah, so x equals n pi.
So it's on the screen.
Okay? Simple, right? You guys understand that concept of n now? It's just an increasing number, including 0. It's an integer value. Okay, maximum and minimum values. Where will they occur? That's one we left out of our review, remember? In chapter 5, any local maximum on an original function is what on a reciprocal function? Yeah, it's a local minimum. Remember, they switch. And that's because if we're increasing, we're decreasing on the reciprocal. So that's why when we switch from an increasing to decreasing, we have to switch from a decreasing to increasing on the reciprocal function. Okay? So maximum and minimum values are going to occur then, not the same, but at the max and minimum, well, yeah, the same in the sense of the original function. Okay? How can we express that now with an n term? Here, I'll write it down. It's not as simple. I'm gonna write it down over here. We can say that max values occur at Okay, so I've actually given a coordinate point now. As you can see, all of the values on the graph here occur at the y point. The max values occur at all y1, 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 and -1 are the minimum values. So I know the y coordinate of the maximum and minimum values. The x coordinate now is again going to be dictated where we're using that n value. Okay, so we have to understand where that comes from. How can you create this equation? You have to look and see how this relates to the graph. So if I plug in 0 for n here, it would be -pi/2. So -pi/2 is a minimum value on the original function. So on the reciprocal function, it's a max value. If n is 1 now, I'm going to have -pi/2 plus 2 pi. That's going to give me 3 pi/2. So if I go to 3 pi/2, I also see that it's a minimum value. You guys see how that works? So it takes a little bit of practice, but it's important at least you understand the concept of how this n value is relating to how you get these values and how it's reproducing them all. You understand that? Any questions? Okay, because it's not going to be necessarily very easily at first. You're going to have to kind of play with these formulas. The key is to kind of start with the first value and think of it when n is 0. You need to get the first one to work. And then you can work on this. Usually it's the amount of time that they take to repeat. So here you can see it's every 2 pi. You see that? So we put the first one in, -2 pi, and then it repeats every 2 pi. Okay, positive and negative intervals. These are going to be the same, right? So these are the same. And they're going to be between positive is between 0 and pi, 2 pi to here, from -2 pi to -pi, these are positive, okay? So you would need to work and develop an n formula for the positive and negative intervals. Okay, I think I can write one of them here. So 2n pi x is less than . So the graph is positive over this interval. So 2n pi, so if n is 0 here, we would have where it's greater than 0, but less than pi. You guys see that? So there's my positive interval, greater than 0, but less than pi. If n is 1, it's going to be, sorry, n is, let's say, -1, it's going to be greater than -2 pi, but less than pi, -pi. -2 pi, less than pi. Those are your intervals. Any questions there? They're tricky. Took me a little while to come up with these. Intervals of increase and decrease. So of course these are going to be opposite on the reciprocal function, right? So where it's increasing would be from -pi/2 to pi/2. That's increasing. So on the reciprocal function, it would be decreasing here. Okay? Points of intersection. So every point where y is equal to 1 or -1, they're going to intersect. Okay, so this point here, this point here, this point here, this point here is where they're going to cross. Or touch. I shouldn't say cross. They don't have to cross, but they need to touch. Any questions of that? Okay, use your predictions in part A to sketch the graph of y equals 1 over sine x. That is, y equals cosecant x. Verify your sketch by entering into a graphing calculator. Compare the period and the amplitude of each function. So, I'm going to try to recreate this graph, and I find this is probably the easiest way to do it. So my zeros, I'm going to put in my vertical asymptote. So here, okay, so those are my vertical asymptotes. I can't touch those. My my points that are the same, y is equal to 1, this is going to be the same on my reciprocal, so I know there's a point there. I know there's a point here. I know there's a point here. And I know there's a point here. So I made my y-axis a little bit larger. Okay, everybody understand up until there? Okay, this is how I do it anyways. I draw the points that I know it has to touch. Now, these values have to be positive because I'm positive in my original function, right? So I can't start to come down here. I also know that this point is a local maximum on my original, so here it's a local minimum. So I know that this has to look like this. You guys understand that? There's no other way I could draw it. This is a vertical asymptote. I cannot touch it. This is a vertical asymptote here. Can't touch. This is a minimum point because it's a maximum point. My values are positive. My values are all positive. The last thing to check would be increasing, decreasing. Decreasing, increasing. Do you get it? So if I draw this one, local minimum, local maximum, vertical asymptotes has to look like this. Has to look like this. Has to look like this. There it is. Any questions? Okay. The next question says, compare the period and the amplitude of the function. So, it's tempting for some of you that might tell me that the period of this is pi. Please don't do that. It's not. Okay? Remember, a period, you have to go back to the one full cycle. So the exact same spot. So the period in this is actually what? Yeah, it's 2 pi. Good. Because until I go to this point again, it's up here, right? This point is this point. So I have to go 2 pi over. Okay? So here is my period, right? Okay, so the period is the same. And the amplitude. Is there an amplitude here? No. Okay, so our amplitude on our original function was 1. Here it's undefined. Our period on the original function was 2. Here it's also 2. Okay, so what do we notice? The periods are the same. The amplitude is not. Question? Okay. All right. Next one. Predict what will happen if the period of y equals sine x changes to 2 pi to pi. Change y1 and change and discuss the results. So, let's go back to our new graph. What do you think is going to happen? So on our original graph, I'll do it here, y equals sine x. Sorry. On our original graph, if y equals sine 2x, everybody understands that this period now is 2 pi divided by k, which is 2, so the period is pi, right? So if the period's pi, that means I go through one full cycle when I get to pi. So my new graph looks like that. Agreed? Everybody understand that? Okay. So now the question says, what will happen to this graph if my period or my graph looks like this? Y equals cosecant 2x. Who thinks they know? Who wants to tell me the answer? What's it going to look like? Remember, our period was the same for the original functions. Now I've compressed it, right, by a half. So I'm going to do the same thing on the reciprocal, right? The period will be now not 2 pi, but the period's going to be pi. So period is going to equal pi. So what does that mean now in terms of my graph? That means I have to go through 2 of these loops before I get to pi. So this whole thing gets compressed down, okay? Because I'm not a very good drawer, I'm going to show you what it looks like. So there's the one I drew. Sorry, that's secant. There's the one I drew. Okay? When we go to 2 pi, it looks like this, because we need to go through both the positive and negative values by the time we get to pi, because the period is now pi. Any questions about that? You see how the whole thing's been compressed from there to here? It's been compressed. Just like what happens with the original function. Alright. Next, we look at the exact same example now, but we're dealing with cos x. We're going to go quite a bit quicker. Okay? It's pretty much identical. So it says repeat parts A to C. So we figure out the y-intercepts. We figure out when the y values are the same, 1 and -1. We figure out the minimum values or maximum values. We figure out that the zeros on the original are vertical asymptotes. And we actually end up with this graph. Okay? Through the exact same reasoning and logic. Remember, cos and sine are pretty much the exact same graph, just with a horizontal translation. Okay, so as you can see from the graph I drew, or the other graph, it's just been shifted over again, right? Same idea. This has been shifted over 90. So that is now on the origin. See that? The period's the same. Okay? If we compress it or we change the period, the same thing happens. It gets compressed. So we have to go through the positive and negative values by the time we get to pi. Any questions about that? Okay. Last one is our tan graph, which the original looks quite strange. Okay. We do the exact same things now. So where there was a 0, there's going to be a vertical asymptote. Where there was a vertical asymptote, now there's going to be a 0. Right? That makes sense? The reciprocal of 1 over 0 is going to be 0 over 1, so it's going to be 0. Where we had our y values as 1, we still have our y values as 1. Okay, so we take all of that information, all of those changes, all of where it's positive, it stays positive, where it's increasing is now decreasing, and our graph looks like that. Looks very similar, it's just kind of flipped. Right, so let's look at the things that are the same. So between pi and 0, the values need to be positive. Between pi and 0, or sorry, between 0 and pi over 2, 0 and pi over 2, values are positive. Values are positive. Always increasing, always decreasing. Vertical asymptotes, zeros. Zeros, vertical asymptotes. Okay? Not hard, or it doesn't take very long to go from here to here once you apply all the rules that we've gone over. Any questions about that? Okay, that's the end of the lesson. The homework is not we'll go through the summary page. Last page. Each of the primary trigonometric graphs have a corresponding reciprocal function. There they are. The graph of a reciprocal function is related to the graph of its corresponding trigonometric function in the following ways. The graph of the reciprocal function has a vertical asymptote at each 0 corresponding to the primary function. So this is all from the beginning that we said. Zeros go to vertical asymptotes. The reciprocal function has the same positive intervals in the corresponding primary trigonometric ratios. So positive values the ranges of the primary trigonometric functions include 1 and -1, so a reciprocal function intersects its primary function at the points. So y equals 1, y equals 1, y equals -1, y equals -1. Exactly from the review from chapter 5. The primary trigonometric function as local minimums corresponds to local maximums. Trigonometric function local maximum correspond, so max values okay, there's your graph. Very, very neat, beautifully done graphs there. Excellent. That's what you want to try and reproduce when you're doing your tests. Okay, you can see both of them. The blue is the original, overlaid with red with the reciprocal function. And this is a beautiful graph for many reasons. You know, 2 colors, very well done. But you can see everything that's happening, right? It crosses the 0, vertical asymptote. Minimum point, maximum point. Sorry?
So I think that's the only time you'll see graphs that beautiful.
Okay, good one, Luigi. Cosecant. It has vertical asymptotes at the points where sine equals 0, has the same period, and the domains are here. So, very important for you guys, again, to go over these domains and see how they use this end term, how they used it to create, you know, these areas where they're vertical asymptotes. Okay, this one's easy. This one a little more complicated, right? They're looking for the domain of the cos value. They're saying theta can't be 2n minus 1 pi over 2. It's important to understand what this means. Any questions?